So in this part of the test review, I want to focus specifically on nomenclature for the test that's coming up. So in this this problem here, we have a mix of different functional groups. One thing to appreciate about the nomenclature that's used in IUPAC is that the name tells us all these sort of different little pieces of the structure. And let's just sort of quickly break one of these down. Let's look at this one. So the ene portion tells us that it's an alkene, okay, so it has a double bond in it. The but portion tells us there are 4 carbons in the longest carbon chain, okay, so that's focused. It doesn't include any kind of substitution groups if there's any kind of branching that might be coming off that chain. And then up here, these are the substituent groups. In this case, there's only 1 chlorine. And then the numerical values tell us where, or 1 tells us where the chlorine is, and then 2 tells us that the double bond starts at the number 2 carbon. And then finally, the cis, and this is, for us, unique to alkenes, there's some stereoisomerism that we have to worry about. So there's cis and trans, so it tells us how do I want to structure my the groups around my double bond. Now for an alkene, when I'm going from the name to the structural formula, there's something that's sort of unique to it, especially in this one. We have that stereoisomerism. Now, the cis orientation, I want to really kind of get that out of the way first. I want to focus on the double bond. I want to make sure that I get that correct. Now, like I said, I know that on the number 2 carbon, that's where I have, that's where the double bond begins. So that, let's say that's going to be the number 2 position there. Okay, so that's number 2. That would be, give that number 3. And so if there's 4 total, then you have 1, 2, 3, 4. Okay, 1, 2, 3, 4 is what we're going to see. And the reason why I'm going in this particular pattern is because that's what gives me the cis orientation. So if that's all the carbons in my structure, then I'm going to have 2 hydrogens sitting up there, right? That's cis. When you have 2 of the same thing on the, one side of the double bond, that's my cis stereoisomerism. The trans would be a situation where one of these hydrogens, they would be down here and they would be on opposite sides of each other. And then after that, I want to fill in the rest of the information. So the only other thing that really stands out is that 1 chloro. Well, if that's my number 1 carbon, then I can just do a chlorine there. And then since I'm choosing to do like a sort of a mix of condensed and structural and expanded structural formula, then I want to go back in and ink in the hydrogens. So what I mean by that is this carbon has 2 bonds to it. So that means that to finish out the octet for the carbon, i.e. 4 bonds, which carbon always has for us in this class, then I have to have 2 hydrogens attached to it. Here has to be a CH3. For these 2 carbons, they were already taken care of by the hydrogens there and the double bond. Right? So that's carbon 1, 2, 3, 4. If I was to draw this in the bond line structure, cis bond line looks like that, and then I can add another bond to then add the chlorine. 1, 2, 3, 4. That would be 1, 2, 3, 4. Last comment, it's not unusual to open up the structural formula around functional groups. On this one you have to, because again the cis notation needs to be shown. Now I won't do a full breakdown on the other ones. So cyclopentane, that's going to be the longest carbon chain. Right? The cyclo means there are 5 carbons. There's a little 5 carbon ring there. And then 1,2-dibromone. It doesn't really matter where I start here. I'm just going to choose a point, 1, 2, and both of those positions are bromine. Right. 1, 2. 3-methylhexanol, so hexanol, we got 6 carbons there, and I'm just going to do the skeletal formula, or another phrase for it is the bond line formula. So I got 6 carbons, 1, 2, 3, 4, 5, 6, okay. There's an alcohol there. The OH tells me there's an alcohol. There's no numerical value in front there, so that means that it's on the number 1 position. And I can choose either one of these end carbons as the number 1 carbon. I'm going to choose here just arbitrarily. Now, one thing you want to watch out for, you don't just want to put a OH there, a hydroxy group there. That would actually shorten the chain, right? I already have 1, 2, 3, 4, 5, 6 carbons. I don't want to lose any, so I need to add another bond going out to that OH group. And then since I chose to put the OH over here, that means that's the number 1 carbon. 1, 2, 3. That's where the methyl is going to be poking off. That's it. And then finally, for this one, toluene, that is one of the aromatic compounds to know. You can leave it like that. A lot of times you actually see the CH3 inked in. So it's one of the simpler aromatic compounds, right? It's just a benzene ring with a methyl group attached. For this part of the nomenclature, we're going the other way, right? We're going from the structure to the name. Now, whenever you're given a structure, one thing you have to decide: do I need to number the longest carbon chain, and how do I number the longest carbon chain? So in this ring structure, the longest carbon chain is right here. There's 6 carbons making up that ring structure. And for this example, we have a functional group sitting there. If you have a functional group, that is the point that is going to dominate the structure. Okay, so that's going to be given the number 1 carbon there. And then I have to decide, do I go that direction or that direction in my numbering? Well, the rule is you go toward the first branching point, the closest branching point. So that means that's going to be the number 2 position. When that line just ends there, what that means, there's a methyl group sitting there. So this is going to be 2-methyl cyclohexanol. There's no need for a 1 here. It's understood based on the ring structure. Now notice this ring and that ring look a little similar, meaning 6 carbons in a cyclic structure, but when you have that alternating double, single, etc. Bond formation, that's actually an aromatic ring. So this is not a cyclohexane. This is not cyclohexanol. For an aromatic compound that's an alcohol, it is known as phenol. And then just a heads up, something I did on the last example. You can choose to put the alternating double single bonds in there or just a circle. What we say is the pi bonds here are delocalized over those 6 carbon atoms. And they basically make up what looks like a donut, a ring of electron density above and below the carbon framework here. And so that ring is often just designated as a circle. For this one, longest carbon chain is going to be found within the ring. So let's get what I call the parent name down. That's cyclopentane. Right, all carbon-carbon single bonds. That's the ane, 5, penta, ring structure cyclo. And then on this end, what we have here is actually, this is the isopropyl group. And since there's only 1 substitution group coming off of the ring, you don't actually need to put a number there. So isopropyl cyclopentane. Right, just break that down a little bit. The prop, that means there's 3 carbons there. 1, 2, 3 carbons. And then the iso, that's the example where the 3 carbons are bonded right in the middle carbon there. For this example, so it's an alkene, so you always want to think about, is this cis trans? And I'm just going to go ahead and say it. It is. You got hydrogens on opposite sides here. This is trans. So, well, that's going to be in the first part of the name. Let's just go ahead and add that. When I number this compound, well, my longest carbon chain is snaking off this way. Okay, and I got to decide, do I start numbering it here or there? Now, I do have a branching point very close to this end, but that doesn't matter here because I do have a functional group. That's more important. The functional group is what's going to dictate my numbering. So notice if I count in from this end, 1, 2, 3, okay, versus 1, 2, 3, 4. The rule is we want to number it in a way to where we reach the functional group as quickly as possible. Okay, so 7, that's going to be heptene in a minute. First off, I have to notice that I do have a methyl group coming off of the number 6 position, and that's really the only substituent group. Okay, so 6-methyl, and okay, so the double bond is at number 3 position. I do need a numerical value in there to tell me where my double bond is. The nomenclature in these two questions dealing with chapter 12, and specifically like aldehydes and ketones. So here we have an aldehyde, right? There's our carbonyl group, carbon-oxygen double bond. If it has a hydrogen bonded directly to the carbon, it's an aldehyde. 1, 2, 3, 4. So bute, 4 carbons. And then the ending for an aldehyde, well, it's an Al. I don't have to put a 1 here because it's understood. The aldehyde is always at the first position because it ends with its terminal functional group with that hydrogen sitting there. Right, ketone is the one where the carbonyl group can move within the structure. Ketone, you got to have a number. To finish this one off, I have 2 fluorines here, so both. Oh, I just noticed something. 1, 2, 3, 4, 5. Be careful. Pentanal. And so now I have the 2 fluorines at the 4 position. And remember something that we do here, if we have multiple groups at a single carbon, then we indicate that with like 2 numbers, 4, 4. We also throw in the Greek prefix di for 2 and fluoro. Notice it's fluoro and not flower-o. Okay? Common error. Now here, it's in bond line form. That's not a hydrogen. This is actually a CH3 group sitting here. So this is a ketone. 5 carbons in a row there. And just like we saw a few minutes ago, yes, there's a substituent group right at the end here, but that doesn't matter. It's this functional group that's going to dominate it dominates the, chemical and physical properties. It dominates the nomenclature as well, specifically the naming, the numbering of the longest carbon chain. So at the number 5 position, I have a chlorine. So 5-chloro. And then here, I need to designate where that double bond is, because it can move, right? Or where the carbonyl group is. There's different isomers of this compound where that carbonyl group could be positioned at, well, any of those other carbons, actually. Here it's at the 2. And then penta, just like here, but instead of pentanal, it's pentanone. Right? Ketone gets an one. Aldehyde gets an al. This one here is also a ketone. Cyclobutanone. And then finally, we have an aldehyde. Now this is an aromatic aldehyde. It has a very specific name. This is benzaldehyde here. And it's not just benzaldehyde. We also have this group. And then notice, what is this group? We have 3 carbons. So, we learned that a 3-carbon substituent group, propyl, would be used. But since it's bonded in the middle, then it's isopropyl. If it was bonded on one of the ends, that would be propyl. But this is isopropyl. Now notice that group could be at any position around this ring. Well, as it turns out, it is at the 1, 2, 3rd position. In organic nomenclature, there's also, remember that ortho, meta, and para prefix that can be used to designate the relative positions. So meta is used here. So instead of putting the 3 there, you could just put meta. Or you can say M isopropyl benzaldehyde. That would be enough of a name to indicate the relative positions of those 2 groups. If the 2 groups were right beside each other, so i.e. the isopropyl group in the number 2 position, that would be the ortho. And then if the 2 groups are right across from each other, that's the para positioning. Ortho, meta, para are only used for aromatic compounds that are di-substituted like this. And the last nomenclature here, hexanal. So let's do the bond line form of this. So 6 carbons, 1, 2, 3, 4, 5, 6. Al, it's a aldehyde. And so you can have a carbonyl group here or here. It doesn't matter. Let's just put it here to make it look a little different than what you normally see. That's totally fine. Typically when you're doing this bond line structure, whichever direction the point is going or the line is going, then anything bonded to it is coming off. And then this hydrogen sort of continues a zigzag. Like for example, the 2 and 3, right, where the two ethyl groups are coming off. At the 2 position, since the point of the 2 is going that way, I draw the bond line in that direction. 3 position, point is pointing down, and so I just extend that, do it that way. I think that looks cleaner. Is it incorrect to do the other way, like ethyl group pointing up like that? It's okay, but I don't think it's the cleanest. Acetone, formaldehyde, these are 2 common names for small. In this case, it's the smallest ketone, and then this is the smallest aldehyde. What's the minimal number of carbons needed for a ketone? Well, ketone, that's a carbonyl group that's bonded directly to carbons on either side of the structure. That's the smallest set of carbons that you can have for a ketone. This is acetone. Where I want to go back in and then fix the hydrogens there. If I was going to draw the bond line structure, then it would look like that. Formaldehyde, that's the simplest aldehyde. What's the minimal requirement for an aldehyde? It's something like that, right? Carbonyl group bonded directly to hydrogen. This isn't correct. There's only 3 bonds here. Simplest would be a hydrogen being added there. That's formaldehyde. Basically embalming fluid. And the last one, octanone. Let's do the bond line for this one as well. 1, 2, 3, 4, 5, 6, 7, 8. Now I'm speaking the numbers as I write it, but every time I write this, even if I'm not speaking it, I'm thinking it to keep track of how many carbons I've added. At the number 2 position, that's where my double bond is, my carbonyl group I should say, and I could go in 1, 2, put it here, or 1, 2, put it here. It doesn't matter. I'll just put it there. And then on the 3rd position, 1, 2, 3, then I have my methyl group. And that's it for the nomenclature on the test review.